And here we go. Part 8, folks. So in previous part, we analyzed the first coordinate, right? So we are in a position where we process the first coordinate in memory and we wrote to it. We manipulated that, we compute the value we wanted, we wrote to memory. Now, I didn't mention what this main loop is. Don't worry, I didn't forget that. We are going to mention that briefly later. So now we want to process the y coordinate, right? Well, we can use pretty much the same code, don't we? Because we want to do the same thing on every coordinate, right? So what's the only thing we need to change? Well, we need to change which address we are reading and writing to, right? So if we have our array here, right, so we have x, y, and z. Yes, it's horrible, I know. So you will have to deal with that, right? So x, y, z, w, dot, 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 right? So it continues forever. Not forever, but... So those are the different points. So RCX is pointing here, right? That's where these registers points to. So we process X, we actually now want to process Y. So we want to move it here. Oh my God, that's awful. All right, so we want to move RCX here. So this goes away. So how do we do that, right? So how do you shift a pointer in C++? Well, usually, let's say we have double my pointer, right, equal to something. We don't know, right? So if my pointer right now is pointing to x, the only thing we need to do is my pointer plus equal 1. Why does it do that? All right, equal 1. And now it's pointing to... now it's pointing to y. Cool. Then we can do the same in assembly, right? Nope. What's actually happening here? There is some sugar, syntactic sugar that C++ is doing for us, right? How much is 1? How much memory we are actually shifting, right? So if it points first to x and to y, it means we shift 1 double, right? So 1 double equal 8 bytes, right? Equals 64 bits. But if that was a float pointer, it would shift 1 float, 4 bytes, 32 bits. All right, so what's happening here? What's happening here, that in reality, this function, this increment boils down to this: my pointer plus size of double, right, times 1. Right? So if it was 2 doubles, it's times 2. So that's what's happening. If it's a float, times float, right? So it's computing how many bytes it needs to shift for, right? So when we add 1, so we shift a pointer by 1, we are shifting by 1 byte, right? So we need to handle this manually. Assembly doesn't do that for us, because assembly has no idea. It just sees zeros and one. It's not no idea what that value is, right? It just sees a number and has no idea if that is a pointer in the first place, and then if that pointer points to a double, or to a class, to whatever, we don't know, right? So assembly doesn't know. So we need to handle that manually, and that's exactly what we are going to do here. So we are adding to RCX, right? So addition, this is the integer addition, right? Because we're using the integer registers, the general purpose registers. So RCX, we are adding to RCX 8, right? 8 bytes, so 1 double, and storing the result into RCX. So we are shifting RCX, right, by this amount, which is, oh my God, that should be an 8. Sorry. 8 bytes. All right. So that's what we're doing. We shift RCX by 8 bytes. RDX, same thing, but we're shifting by a float, right? So 4 bytes. So we're shifting by 4. So now RCX points to the correct value, RDX points to the same value, correct value, and you see we can execute the same code, right? If we wanted to, we could switch that into a function and call the same code, right? But of course, we pay the function call. So what we're going to do, what I did was just lovely copy paste it. It's the same Excel code. We load the value into a register, we convert the normal, we scale the normal, we sum, and then we write to memory. And you guessed it, Z is the same exact thing. We increment by 8 the points, we increment by 4 the doubles, sorry, the normals, the floats, and then same exact code. All right. So after on line 43, what happened is that we processed Z. We processed X, Y, Z. So we are ready to process the next point. We processed a full point also, right? But hold on a second. We are not going to copy paste this code for all the points, right? Well, we could if we had a fixed point. So a fixed number of points. Like if we know for sure that number of points is 64, 1024, 104, or a random value, we could copy and paste this instruction for the number of time we want. And that's what is called loop unrolling, right? But we don't know. So that's very same reason in the C++ code, what we do is a loop for the number of points. We need to do the same exact thing. How do you loop in assembly? You do that with gotos. I'm pretty sure right now C++ or C programmer dies somewhere in the world because I said the word goto, right? So goto is bad in C and C++. Is if you write one, you're shamefully pointed out and every colleague will laugh at you, right? But that's how assembly works, right? Shifting, so jumping, right? So you perform a jump, and where do you jump to, right? So assembly allow us to define labels, right? So label is defined like this, called main loop. This is my label. So you write the name of the label, we can do whatever, just loop or my awesome label, right? Whatever. And then you ended up with a column, right? So that's how you define it. So next, we can jump to this label if we need to, right? And we're going to see how to do that. But before jumping back here and repeating this code, we need to point RCX and RDX to the right place, all right? So RCX is pointing to Z. So we want to skip Y, and then we want to go to Z. So we need to skip 2 floats, right? So we need to shift by 64 bytes. And that's exactly what we're going to do. We are shifting by 16 bytes. We are skipping W, basically. And instead, the normals, we don't need to do that because the normal, if you remember, is XYZ. XYZ is stride 3. So we just increment, and now RDX point to the next one. All right, cool. So we did the first iteration of our loop, right? So what we're going to do next, we are decrementing R9. You might wonder, what the heck is R9? If you don't remember, is the point count, right? Since we processed one, we are going to decrement the counter, right? So dec is an instruction. It means it's the same thing as doing R9 minus equal 1. That was decrement thus decrement by 1. Now what we are going to do is compare instruction. Okay. So the compare instruction, what it does is it compares the first operand with the second one. And what it does, it sets some flag in the processor, and we can use that for perform jumps, right? Sounds a bit strange, but let's try to figure out what's happening here. Here, I'm comparing the value R9 with 0, right? So basically means the same things as if point count equal to 0, then we break. We exit the loop, right? And if that happens, if it's equal to compare is equal to 0, a flag in the register, we're going to see which flag So the 0 flag is going to be set to 0, and other flag, maybe if it's negative, is positive, so on. It's going to be set. And then we can use those flags to jump. So in this case, I'm using jump if not 0. J and Z means that. So if the value is not 0, so the value we just compared is not 0, so the 0 flag is not set, we want to jump. Where we want to jump? To main loop, right? So this is the mnemonic value, which basically is going to be replaced by the address of the first instruction after the label. So it means we are jumping to line 18. And you guessed it, we are going to process X, Y, Z, shifting the pointer, decrementing, and jumping. All right, so you see that is a loop, right? We keep jumping until we didn't process all the points, right? So that's might make you wonder, hold on a second, in a for loop, after each iteration, is there actually an if statement? Yes, there is an embedded if statement, which is basically evaluating this to know, do we need to loop more? Yes or no? That's how a loop works, right? So we don't see that in C++ because that's taken care of for us, but that's how you loop in assembly. So let's say that R9 is equal to 0. This is not going to jump because it's not is 0, so the jump condition doesn't trigger, and we just return. Ret means return. It's really important that you return, otherwise we are not going to jump back to the callee, to our caller function, right? And we will just keep going down to the next instruction, which is bad. You will get an hard crash without the return. So that's it. That's our code. That's how it runs. That's how we loop, right? So the video took actually longer than I expected, so I don't want to make it too long. So in the next video, the only thing we're going to do, we're going to follow this code step by step, right? Until basically seeing the register, what happens, and so on. Okay? So guys, see you in the next video.